Welcome to this explainer. Today, we're unpacking something pretty incredible: how the Aurora framework takes this highly complex zero-knowledge cryptography and makes it absolutely production-ready, right on the Solana blockchain. Let's get into it. Okay, so let's just dive right into the core tension here. You see, Solana is an incredibly fast network, right? But native zero-knowledge math, it is incredibly heavy. When you actually try to run those complex cryptographic proofs natively on-chain, it completely exhausts Solana's strict compute unit limits. Think about it like trying to run a supercomputer simulation on a pocket calculator. The network just simply wasn't designed for that specific type of heavy lifting. So to understand exactly how Aurora solves this puzzle, we're going to cover 1. The ZK compute bottleneck, 2. Aurora's layered architecture, 3. The life cycle of a proof, 4. Testing cryptographic boundaries, and finally, the developer experience. All right, section 1. The ZK compute bottleneck, or why Solana needs a little help with ZK math. Just to make sure we're all on the same page, a zero-knowledge proof essentially lets you prove you meet a certain condition, like, say, being over 21, without ever showing your actual ID, your birth date, or your name. It's really the holy grail for digital privacy. But, and this is a big but, generating and verifying that proof, it requires massive mathematical overhead. Take a look at the initial readiness score we have here. Aurora started with a pretty solid baseline of 85 out of 100. They had good documentation, a functional architecture. But in the world of high-stakes decentralized systems, good enough testing and standard execution just won't survive a real production environment. The margin for error is literally zero. They needed a way to scale this without crashing the network or, leaving any subtle vulnerabilities behind. Moving on to section 2, Aurora's layered architecture, the 3-tier off-chain solution. So check out these 3 distinct layers. You've got a WASM-powered client SDK sitting on top, a Rust-based off-chain verification daemon right in the middle, and finally, the Solana on-chain anchor programs holding down the base. Now, WebAssembly, or WASM, is the absolute magic ingredient here. It acts as a critical translator, letting the high-level TypeScript SDK consume compiled Rust code, meaning all that complex math can be executed at near-native speeds right inside your browser, which completely removes the generation burden from the blockchain itself. How cool is that? Okay, section 3, the life cycle of a proof. Let's follow the data journey. This data's sort of hero journey has 3 key steps. First, the proof is generated at the edge, meaning it happens locally and completely securely on your own device using that WASM SDK we talked about. Your private data literally never touches the internet. Second, it's verified off-chain by the Rust daemon. And third, only after it gets past the daemon, it's submitted to the Solana Anchor Registry for a final low compute attestation. The ledger becomes this immutable record of truth, but it is completely freed up from having to do all that heavy cryptographic math. So, the really crucial point to grasp here is that the off-chain daemon acts basically like a super strict nightclub bouncer. It stands firmly between the user and the blockchain. Before proof ever even reaches the Solana network, the daemon executes this high-speed mathematical check. If a proof is malformed or worse, fraudulent, the daemon just blocks it. This keeps all the junk data out of the Solana VIP room, it protects the network's runtime from denial of service attacks, and crucially, it saves you from wasting gas fees on transactions that were destined to fail on-chain anyway. Section 4, testing cryptographic boundaries. Let's talk about moving beyond just good enough. Check out the stark contrast in testing methods here. Standard unit testing, it just checks if code runs on a typical happy path using predictable inputs. It asks, hey, does this function work when I type the number 4? But property-based testing, or PBT, it is a totally different beast. It defines universal mathematical rules, invariants that absolutely must always be true. Then it just bombards the system with thousands of random, dynamic inputs every single second. It acts as an active adversarial tester, looking for that crazy needle-in-a-haystack logic error that a human developer would frankly never think to script manually. By really aggressively expanding their testing matrices to include extreme edge case bounds, they look for exactly where the system truly breaks. We're talking about hitting the system with empty inputs, null proofs, and maxed out numeric limits, just to check for integer overflows. The ultimate goal here is to ensure that when the system does finally hit a limit, it fails safely and gracefully with a crystal clear error, rather than just crashing the whole shebang or leaking sensitive state data. And right here, you can see their custom security simulation actually in action. Now, in cryptography, one of the absolute biggest threats is a replay attack. That's where an attacker intercepts a valid, previously used proof and tries to inject it again to duplicate a transaction or to gain unauthorized access. Well, Aurora built a custom Rust simulation that actively tries to replay proofs against itself. The system instantly identifies the unique hash of the duplicate proof and just gracefully rejects it. This takes their security posture from just being theoretical to being empirically validated. Because they mapped these highly advanced testing methodologies across both the Rust and the TypeScript components, they essentially created an ironclad continuous integration pipeline. Every single time a developer pushes new code, GitHub Actions triggers this massive suite of property-based, edge case, and security tests. It acts like an unrelenting, automated referee, making sure there is zero regression in the codebase. And thanks to that incredibly active adversarial testing posture, Aurora skyrocketed their test coverage score from a standard 80% to an elite 95% logic coverage. They didn't just verify if the code executed, they completely proved the mathematical boundaries were sound. All right, Section 5, the developer experience, making the invisible visible. By abstracting some really highly fragmented setup scripts into a single root makefile, they dramatically accelerated the time to first value for evaluators. Before they did this, developers had to manually install Rust toolchains, they had to pin specific Anchor CLI versions, and juggle all these NPM installs across different folders. Now, they simply type make all into their terminal. That's it. It's a single entry point that installs dependencies, builds out the Solana modules, and runs the entire testing suite. They basically eliminated environment configuration as a barrier to entry. Furthermore, they built these incredibly interactive CLI and web interfaces with clear, color-coded feedback, which makes the notoriously opaque black box of cryptography completely grokkable for anyone. Instead of forcing evaluators to parse through these dense, boring terminal logs, they offer a sleek React web demo. Users can just type in their public and private inputs, click generate, and literally watch the lifecycle happen, transitioning from local processing to off-chain daemon validation, all the way to a satisfying green success box when it successfully hits the Solana chain. It makes all that invisible math entirely visible. So, as you can see, every single strategic intervention stacks up in this readiness waterfall. From that comprehensive testing we talked about to the unified makefile and the tangible demos, they all stack together to transform what was just a basic hackathon prototype into a rigorously tested production-grade framework. And it all culminated in a massive final readiness score of 92 out of 100. This foundation is absolutely incredibly powerful because it genuinely opens the door to some massive real-world applications. Just imagine privacy-preserving KYC, right, where you can prove your residency without actually exposing your home address to anyone. Or under-collateralized DeFi lending, where you can run a local proof of your creditworthiness without having to publish your private bank statements to a public ledger. It enables completely anonymous but mathematically verified governance voting, confidential supply chain auditing, and highly secure enterprise data access. The ledger stays public, but your data stays private. The invisible has truly been made visible, and more importantly, verifiable. By using WASM at the edge and a Rust daemon to protect the chain, Aurora has fundamentally solved the compute bottleneck for zero knowledge on Solana. So, this leaves us with one final question for you. With that friction finally removed, how will you use this framework to bridge the gap between absolute personal privacy and global blockchain ledgers? Thank you so much for joining me on this explainer. Keep learning and happy building.